So far we've talked about x-axis revolution. And what I mean by that is when we have some sort of shaded region here, when we're finding the volume when it's revolved, we're revolving it around the x-axis. But if we decided to instead revolve it around the y-axis, so if instead of slapping it and having it spin this way, I slapped it but it spun around this axis, I would generate a different solid. I would generate, instead of this x-axis revolution, generating this large radius, kind of creating a sort of a fat base and skinny height, when instead I would have, with the y-axis revolution, would be a skinny base and a tall height. You can see that here, right? If I spin that, it has a radius of 3, but has a height of 15, versus if I spin it here, it has a radius of 15 and a height of 3. And we can evaluate these areas as well, volumes as well. Pi 15 squared times 3. So this is 675 pi. And doing here where the radius is 3 but the height is 15, you get 135 pi. So you get a difference of about 5. One is 5 times more voluminous than the other. And that's kind of an important result, because what it tells us is that how we revolve these things, the axis that we revolve it, affects the volume that we're going to get, which is kind of natural, right? Because in this particular case, notice that the strips are a lot more close to the y-axis than they are to the x-axis. This is really far away from the x-axis. So the further it is away, if I take that and I spin it all the way around, right, it takes a lot of volume to go that whole range, versus if it's really close to the axis, it's just little bitty spins. So this is what we want to do. How are we going to do this? If I have some function and I want to revolve it around the y-axis, how am I going to do this? Well, in the x-axis revolution, we took those disks and we summed them up from the x-axis to the function. We kept summing them from the x-axis to the function. What we find for the y-axis revolution is we're going to do the same thing, but instead the disks are going to come from the y-axis to the function. Now to do that, we've got kind of a problem, because our function heights are defined in terms of their distance from the x-axis. So we need to find a way to determine their distance from the y-axis. And the way we're going to do that is we're going to sort of find those inverse functions where we can write them in terms of y inputs instead of terms of x inputs. So if you go all the way back and learn how to find the inverses of functions, assuming that the function is invertible, then what we'll do is we'll say, okay, we need to take some function and we need to rewrite it in terms of y. And I'm just going to call this h of y. You don't have to call it h of y, but I'm going to. And then what we need to do is we need to find the y bounds, right? So in this particular case, we go from 0 to 3 on the x, but if we're writing in terms of y, we have to go from the low bound to the high bound. Or you might sometimes think of this as the high to the low, because you're going this way, but most of the time it gets a little dicey. You're better off just going low to high here. So in this particular case, it's very clear that we're going from 0 to 15 in the y case. So once we find the y bounds and we rewrite this, and we're going to talk about how to do that in a minute, we have a new volume function. And the volume function is exactly the same as what we're used to. It's the integral from a to b of pi times that function squared. So instead of f of x squared, it's just this h of y squared. And we're integrating with respect to y because we're changing over the y values instead of the x values. So it's the same idea, we're just changing up the function a little bit. So for this particular example, we start here. We say, okay, my function is 15 minus 5x. Okay, so how do I write that in terms of y? Well, if you go back to your studies in sort of algebra, maybe pre-calculus, about how to find inverse functions, you recall that you write that as y equals the function, and you try to get that x by itself so that everything is in terms of y. So we would subtract 15 from both sides, and then we would multiply by a -1 here, and then we would divide everything by 5. So I now have some x equals a function of y. So that makes h of y equal to this quantity, 3 minus 1/5 y. Now we know that y starts at 0 and ends at 15. We've talked about that already. And then from the volume, we use this formula. We go from 0 to 15, those are our bounds, pi 3 minus 1/5 y squared dy. Now, what we can do from here is we can, what I did at least, is I performed a u substitution. I let u equal 3 minus 1/5 y. And I'm not going to walk you through these steps. I'm kind of expecting you to be a little familiar with the substitution method by now. So if you perform that substitution, you end up with this integral, which when computed will achieve 135 pi, which of course is exactly what you would expect because that's what we developed when we did this with standard geometry. Now again, the whole point of doing this is to do this with functions that classical geometry cannot give us, or at least would not be intuitively obvious to give us. So we're going to do another example with a different function, and let's see if we can't put this method to use.